Hello and welcome to C and Data Structures training session. In this session we are going to learn about a data structure called linked list. So in this session we are covering what is linked list, what all are the terminology that we used in linked list. We will be learning about how to create a linked list and how to do operations on linked list. We will be learning about how to do traversal in the linked list, and then we will be learning about what is doubly linked list and circular linked list. So let's begin. So what is a linked list? A linked list consists of a sequence of nodes. So what is nodes? Node is a segment of memory. Uh, so here this is a segment, memory segment, this is a memory segment, this is a memory segment. So linked list is a sequence of node. Node is a section of memory. Each node contains a value. So every node has a value and a link which is pointing to some other node. So this is the link part which is pointing to some other node. So that is why it is called a linked list, because each memory section is linked to some other memory section. So it's a chain that is being built upon, and the last node will contain a null. So this is how our chain terminates. So let's reiterate. Each node in a linked list has two sections. One is a data section, one is a link section. Each link points to some other node, and which constitutes the chain, and uh, that is why it is called linked list, because there is a link between one node to another node, and it's a linear format, so it is called a list. So linked list. So the list may have a header. uh, it's good to have a header. Header is nothing but it says that from where my linked list is starting. So generally it contains the location of your first node. So here is a starting element of the linked list, or I can say the head of the linked list, which contains the memory address of the first node. So this is the linked list. This contains the first address of the first node. Then node A has B as the next node, B has C as the next node, C has D as the next node. So what is the terminology that we used in linked list? A node's successor is the next node in the sequence. So the next node in the sequence, this is the successor of uh, the node. So B is the successor of A, C is the successor of B, and so on. The predecessor is the previous node of the sequence. So A is the predecessor of B, B is the predecessor of C. The list length is the number of elements in the list. So in this linked list we have 4 nodes, 1, 2, 3, 4. So the length of the linked list is 4. So this is what we used to call or we frequently use these words in the linked list. So let's touch upon how to create a linked list. So let's assume this is a linked list. Linked list has, as we have covered, that this is the memory segment, which is also called node. Each node is a structure uh, which has a value and a pointer to the next node. The pointer to the next node is nothing but a pointer to the same structure. Uh, the data part or the value part, whatever we call it. Here we are using an int value, but it could be anything. It could be another structure, it could be another string, character array, it could be anything. So whatever we store here is a data, which could be anything. Here we are using integer. Whatever we store here is a pointer to another structure which stores the address of the next node. So this is how we define a node. Uh, to assign a memory to a structure, we have to use malloc. So this is how we assign a memory to the structure. Initially, when we declare any structure, it won't be assigned any memory. So we need to allocate some memory to the structure. So this is how we do that. Then once the memory is allocated, how we access the value part of the linked list is temp and this operator arrow, this we call as arrow operator, which is nothing but hyphen and a right arrow. So this is called an arrow operator, and temp arrow value. So temp arrow value will help me to access the value portion of the node, and we can store the value like this. So this is how we can assign the value. Okay, this is how we can access the next element of the, or the link part, or the next part of the linked list. We can assign it to some other node, or we can assign it to null. Okay, so struct node my list equal to temp. So here what we did is we created one node, one empty node, and then we assigned the root. This root will be pointing to temp. So temp will become our first node. Let's learn about traversing the linked list. So traversing the linked list is nothing but going through the linked list in a way how we, as and when we get the address of the next part. So for example, we have declared a structure like this, which has in data part as an integer and a next part. Then this is a root element, and then we generally will take a temporary variable which is and we assign it to a root, and then we run a loop which continues until temp is not equal to null. We print the data like temp equal temp arrow data, and temp is assigned to the next element. So temp will be keep on increasing, keep on increasing, keep on increasing, and until and unless temp becomes the null, or because at one point of the time, if we have a terminating linked list, like the last element of the linked list is pointing to null, so at one point of the time we will be hitting that pointer, and we will be getting null. So this loop will end, and we'll end up traversing entire linked list. So let's see how we traverse a linked list. Say this is our linked list. This is a data part, this is a link part. So suppose we have declared a temporary variable this. Now initially we assign temporary variable with a root, which will point to here. Then once we print this, we assign uh, this dot next, which is this, to the temporary variable. Now it will point to here. Again, the next part is assigned to the temporary variable, which points to this part, and again finally we end up getting a null. So this is how we traverse a linked list. So let's touch upon what all are the operations which are possible in the linked list. So there are two operations which are possible in the linked list. One is insertion in the linked list, one is deletion in the linked list. So insertion and deletion could have many flavors. One could be inserting at the end of the linked list, one could be inserting at the beginning of the linked list, one could be inserting at the middle of the linked list. Similarly, deletion could have many flavors, like deleting the last node of the linked list, deleting the first node of the linked list, deleting something in the middle of the linked list, and so on. So we have different flavors of insertion and deletion. So this is we are explaining more about insertion. There are many ways to you might want to insert a new node in the linked list. Insert as a first element, insert as a last element, insert in the middle. How you do insertion in the middle, like before a given element, after a given node, before a given value, after a given value. So there are many combinations that we can try out on insertion. So all are possible, but it depends upon what operation we choose, and each operation has its own difficulty level. For example, adding a node at the end of the linked list is easy. Adding a node at the middle of the linked list is a bit trickier. So it has each and every operation or each and every flavor of insertion in the linked list has a difficulty associated with it. So inserting after, how does this function works? Inserting after. So let's suppose we have this linked list and we want to insert a node 2.5. So find the node that you want to insert after. So let's suppose we insert our node after 2. So here we want to insert after 2. First, copy the link from the node that's already in the list. So you need to copy this link somewhere. Okay. So what we will do is 2.next equal to node.next and node.next. So what will happen is this 2.next will point to 3, node.next will also point to 3. Now we will have to do, we will have to make 2.next points to node. Change the link in the node that's already in the list. So we need to change the link of this to this. First we have to dereference it and assign it again. So this is how we can insert the linked list. So now when we traverse the linked list, it will be like this element, then this element, then this element, then this element. So let's do some practical example. Let's write some code for this. So this is the code for very basic operation of inserting into the linked list and traversing through the linked list. Here we have declared a structure of node. The data part is integer. The next, or the pointer which is pointing to the next node, is next. Then we have a declared two function add, which adds a value to the linked list, and then we have a function called print, which prints the entire linked list. So let's go to these functions, add and print, then we come to main. So first go with the add function. This is our add function. So what we are doing is we are passing a pointer or we are passing the address of the root element, root or head, whatever we call it. Then we are passing the value what we want to store in the new node. So here we are adding a node at the end of the linked list. Just for simplicity, we are doing this operation. So now what we are doing is we are having a temporary node and assigning a memory to it. So we are allocating some memory to a temporary node. The node type should be struct node time. Then we'll be filling the data inside the node. Temp.data equal to value, temp.next equal to null. So why we are making temp.next equal to null? Because we are adding the node at the end of the linked list. So we want this node to be a terminating node. So that's why the next element should be null. Okay, now we are doing some checking, like if our root is null, if value at address root is null, that means our head or root or starting point of the linked list is null, that means our linked list is entirely empty. Then what it will do, it will assign value at address root equal to temp. So temp will be stored at the root, or root will be pointing to the temp. So this is the creation of first node of linked list. Now in case we already have something in the linked list, then what we are doing is we are declaring some temporary variable called list and assigning it to our root. Then we are traversing like this. If list.next is not equal to null, we are assigning until and unless we get some node whose next is null. Okay, once we find that node, what we are doing is we are making list.next equal to temp. So the last element of the existing list will point to the temporary element or temporary node, and in temporary node we already have the next part pointing to the null. So ultimately we end up adding the new element at the end of the linked list. So this is how we traverse the linked list. This is a function called print. It is accepting a root, a root pointer. So struct node, we are declaring a temporary variable here. Then while temporary variable is not equal to null, we are keep on printing the data at the node temp. So we are printing temp.data and incrementing temp equal to temp.next. So we are assigning we are jumping from one node to another, one node to another. So how the jumping works? Jumping works like this: temp equal to temp.next. So until and unless temp becomes null, this loop will continue and we'll exit out of the loop. So how we use this into the main function? Okay, this is the main function. We have declared struct root equal to null. So initially we have declared a root of our linked list and initialize it with the null value. That means our linked list is entirely empty. Now what I'm doing is I'm declaring a variable I which is used for loop. I'm running a loop from 0 to 10 or 0 to 9 and adding I to the linked list. So I am adding 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to the linked list. Then what I am doing, I am printing the linked list. So this is here I am adding elements 10 times in the linked list, one after the other, and here I am printing the entire linked list. So let's see how this program runs. GCC -o linked list.c. So I got a compilation success. Now /linked list. So if I run this program, what I am doing is I'm initially the nodes are getting added and then we are printing. So output of this program is we are printing the linked list. So this is how linked list will behave. Okay. So let's see one more program which is another flavor of adding the value or adding the node in the linked list. So here I am continuing with the existing program that we have discussed just now, and I am adding one more function called add after. So what this function will do, it will add a node after this value. So it will search for this value and add a node which has the data part as this value. Okay, so let's see this function, how this function behaves. Add after, this is a function add after, so I am adding value after x. Okay, so initially we are checking if root is null, that means our linked list is empty, so we don't have anything to add, we'll return safely. Say struct node temp equal to root, we just have a temporary node which is pointing to the root. Now then we are running a loop to find the value x. Okay, so we are doing two things. We are doing temp equal to temp dot next. That means we are jumping from one node to another node until we find null or we find x. Okay, so here is the jumping part, temp equal to temp dot next. Then once we exit out of the loop, we'll check if temp dot next is not equal to null. That means once that means it is, we arrived at a point where it is not the last element of the linked list or last node of the linked list. If this is the case, that means we are adding the node in between. We are declaring a temporary struct node p and allocating a memory to it. Then what we are doing is p dot data equal to value, p dot next equal to temp dot next. Okay, so p will p uh, the next element that will come after p will be temp dot next, and then we are assigning temp dot next equal to p. So temp will point to p and p will point to whatever the temp was pointing earlier. So we have added p in between temp and temp dot next. So that's how add after works. Let's see how we use it in the main function. So this is the part which we have covered earlier. So we have declared a root, we have added 10 elements, we printed the linked list. Now what we are doing is we are adding a value called 34 after 4. Okay, and then we are printing the linked list again. So let's compile and run this program. So we got a compilation success. I named this program as linklist1.c. You can name it with anything you want. So here is the output. This is the first print that we did. Like this is a normal linked list, or linked list where we have added the value from 0 to 9, and then I have added 34 after 4. So here what we got the value 0 1 2 3 4, then 34, then 5. Like earlier it was 4 is pointing to 5, now what is happening, 4 is pointing to 34 and 34 is pointing to 5. So we have added after the particular value, or we have added one node between the two nodes of the linked list. So let's see how deletion works. So in order to delete a node from a single linked list, you have to change the link of its predecessor. So predecessor means whatever node which is before a particular node has to point to the node which will come after the node that we are deleting. So little bit confusing, but suppose there is three nodes A, B and C. A is pointing to B, B is pointing to C. So we have in this case, if we want to delete B, so what we need to do, we need to change the link of A. That means the next portion of A. So A should point to whatever B is pointing to. So now in this case B is pointing to C, so to delete B and maintain the linked list, A should point to C. So this is what we are going to say, the predecessor should point to the next element of the current node. It is slightly tricky because you can't follow a pointer backwards. So deleting the first node in a linked list is a special case because the node's predecessor is the list header. So let's revisit these 2 points. Why deletion is tricky? Because you don't have a pointer to the previous node since it is a singly linked list. There is a cases where we have a pointer to the previous node where we call it, where we have a doubly linked list, which we will cover later. But talking in terms of singly linked list, it is difficult to delete a node in between. So we need to write some logic so that we can have a predecessor's pointer, so that we can manipulate the predecessor's next portion to point to the successor's next portion. Okay. So let's write some code for deleting the node in the linked list. This is the code for deleting the node in the linked list. I have followed the first program that we have written. So we have two methods, add and print. Why we require these two methods is because we need some data in the linked list. So we have these two functions. The new part is this: I have added this function delete node. So what delete node will do is it will delete a node uh, which has value equal to VAL or whatever we will provide in the as a parameter. So let's see this function. So delete node, this is the function delete node. So what we are doing in delete node is we are maintaining two pointers, one is temp and one is previous. Okay, temp will point to temp will be assigned to root, previous is we set previous equal to null. Then what we are doing is we are running a loop to find a node which has value or data portion as equal to val, and similarly we are jumping temp equal to temp dot next, and what we are doing is we are jumping the previous also. So what we are doing is previous is assigned to temp and temp will assign to temp dot next. So we are maintaining two pointers and we are moving two pointers. So we are maintaining a link to a predecessor and we are maintaining link to a successor. So if previous equal to null, then return. That means we don't find anything like our loop is ended and we didn't find anything. So uh, we return safely because there is nothing to delete. If temp dot data is not equal to val, like we found, we our loop is ended, but the pointer which is pointing to temp does the data portion does not match with the value. So that means we reached to the end of the linked list, but we didn't find anything which is matching to value. So again we return safely. If none of the condition matches, then what we do is we make previous dot next. That means predecessor next pointer equal to successor's next pointer. So predecessor dot next will point to successor dot next, and then we will free the memory. So we now temp dot next is will be pointed by previous dot next. So there is no, and we need to delete the temp because temp dot value is equal to whatever value we want to have. So we can free the memory. So that's how we delete it. So let's go through the main function, like how we are using it. So in main function again, what I'm doing is initializing the our linked list from 0 to 10 or 0 to 9, printing the linked list. Then what I'm doing is I'm deleting a node 5 and then again reprinting the linked list. So let's see what happens. Let's run the code. C minus linked list 2. So we got a comparison success. So here, this is the output. So this portion here, this is the first print where we have initialized the linked list and did a print. Now this is the print after we have deleted the nodes. So you can see we have deleted 5 here and 5 is not coming to picture. Earlier 4 is pointing to 5 and 5 is pointing to 6. Now 4 is directly pointing to 6 and we have freed the memory which is holding 5. So this is how we perform deletion in the linked list. Okay, so this is a small animation. To delete the first element, change the link in the header. So if you want to delete the first element of the linked list, our header should point to the successor of the first node. So this is the this is the linked list, and we remove the link, or we this variable does not point to this, but it points to this. So this is now our linked list will be like this. We will not be using this and we can free this memory. To delete some other element, change the link in its predecessor. So like this is the predecessor. So predecessor will not point to this. Suppose we are deleting this node, so predecessor will not point to this, but it will point to this. So this is how we traverse the linked list now, and we can free this memory. Delete node will eventually be a garbage collected, or we need to free the memory so that uh, we don't overuse the memory. If we are not freeing it, it will be held up and will not be it's a memory loss. Okay, so let's touch upon what is a doubly linked list. So doubly linked list is nothing but an extension to a single linked list, where each node will be having 2 pointers. One is pointing to the predecessor and one is pointing to the successor. So here this is suppose consider this node. So this node has now 3 portions. This is a data portion, this is the next portion which is point to the successor, this has one more portion which points to the predecessor. So accordingly we will make changes in the structure. And how the doubly linked list will help, like in case of deletion we need to maintain 2 pointers. Now in this case where we have doubly linked list, and if you want to delete anything, we don't need to maintain 2 pointers. We just find the value which we need to delete and then go. Suppose we want to delete B, we find B and then we go to this element A. Then what we'll do, A dot next will point to C and C dot previous will point to A. So that's how we can do. It's a very simple thing. So each node contains a value, a link to its successor and a link to its predecessor. The header points to the first node and in the list, and to the last node of the list. So uh, header has two information. It depends upon how we build a linked list. It is not always mandatory that header should have information about the last node. Uh, it all depends upon our execution, like how we want to maintain. So it's up to us how we write the program, whether we want to maintain the pointer to the first element only, or we only need to maintain 2 pointers, one which point to the first element, one which point to the last element. So DLLs compared to SLLs. So before that, let's write some code for the doubly linked list. So this is the code for doubly linked list. So as you can see, we have a structure node. Earlier it was having data and next pointer. Now it has a previous pointer also, which points to the predecessor of the node. This points to the successor of the node. Then what we are doing is, while we need to modify add and print function, all not print function, but we need to modify add function also. So let's see how the new add function will look like. So this is how our new add function will look like. Again, here we are just initializing the memory. Now the temp dot data equal to value, temp dot next equal to null, temp dot previous equal to null. So here we are just keeping initializing a node which with the default values. Then we are finding if root is equal to null, that means it's an empty linked list. We are assigning root equal to temp. In case our linked list is not empty, we are having a temporary pointer and finding the and traversing till we reach the end of the linked list. And then what we are doing is temp dot previous equal to list. That means temp dot previous, like predecessor of temp, will point to the this variable list, and list dot next points to the temp. So that's how we add it. And we have also written one function called print reverse, which prints the linked list in the reverse order. So let's see how this code is. So this is a print reverse function. What it will do is, it will just we pass a root to this element, to this function as a parameter. Then we have a variable which points to the root. So first we go to the end of the end of the linked list. Now here in this doubly linked list, we are not maintaining a pointer which points to the end element of the linked list. So if you maintain that pointer, then you need not have to do this step. So since we are not maintaining, we need to find the end of the linked list, and from the end we are jumping backwards and printing the value. So printing the value, jumping backwards, printing the value, jumping backwards until temp is equal to null. So this is how we do operations in doubly linked list. I'll suggest you try this and do some modifications, like add some element in the doubly linked list, delete some nodes in the doubly linked list, and have two pointers which points to start or the first node of the linked list, and one points to the end of the linked list, and do some operations uh, like add the values in the linked list and print the sum and do all kind of things operation. There are number of operations possible in linked list. So let's compare doubly linked list and singly linked list. So DLLs start for doubly linked list. Doubly linked list is short form of doubly linked list. SLL stands for singly linked list. SLL, singly linked list. So singly linked list is nothing but what we have discussed before doubly linked list, where any node points to the successor. It does not have a predecessor node. Okay, so advantages, uh, can be traversed in either direction. So doubly linked list we can traverse in either direction, front and back, uh, but we cannot traverse in uh, from any direction, front and we cannot traverse in back direction in a singly linked list. Some operations such as deletion and insertion before a node becomes easier. So in a doubly linked list, it is easier to perform operations like add some node at the middle of the linked list and delete some node at the middle of the linked list. In the singly linked list, we need to maintain uh, two pointers, which one points to the predecessor, one points to the successor, and then we need to do some operations. So in doubly linked list it is much easier. Singly linked list we need to write some extra code. So what are the disadvantages of this thing? So DLL or doubly linked list requires more space, because now in doubly linked list each node has an extra link which is linked to its predecessor, so it requires extra memory. List manipulations are slower because more links must be changed. So if we want to do some manipulations or want to change links in bulk, this is tedious operation. So greater chances of having bug because more links must be manipulated. So if we perform this operation where we need to change most of the nodes in bulk, it may happen that we end up in some bugs which is not easy to debug. So we need to be very sure what is our requirement, and do we really need doubly linked list? Can we do operation with singly linked list? What is our performance impact in with the time complexity and memory complexity? So we should take care of these stuff before deciding what to use. So deletion a node from a doubly linked list. So node deletion from doubly linked list involves changing two links. In this example we will delete node B. So earlier example we have set of three nodes A, B, C. Now in this example we are deleting node B. So this is our linked list. We are deleting node B. So what we are doing is the link uh, the A's next link which is pointing to B is removed. Now A is pointing to C. C's previous which is pointing to B is removed. C's previous is now pointing to A, and that's how we delete it. So we don't have to do anything about the links for the B, and we can free the memory. Garbage collection will take care of deleted nodes. So we need to free the memory, and then it will be taken by the garbage collector. Deletion of the first node or last node is a special case. So if you want to delete the first node, then what we need to do is this node will point to this, and the previous of this will point to null or nothing. So we need to change the things, and similarly if we want to delete the last node, we need to adjust the pointers accordingly. So other operations that are possible in linked list are like most algorithms in linked list, such as insertion, deletion, and searching are pretty obvious. So you just need to be careful what linked list you want to choose and what operations are required in your program. Sorting a linked list is just messy since you can't directly access the nth elements. You have to count your ways through the lot of other elements. So if you want to sort a linked list, it requires some effort because we cannot directly access the uh, element through index as we can do it in array. We need to traverse through the linked list, find the element, and do the changes. And also we cannot shuffle the value very easily. For example, we can shuffle two values in array very easily, but if you want to shuffle two values, we need to change lot of pointers. So we need to be very careful in that also. So there is a special case called circular linked list. Circular linked list is nothing but it has one head element, and it has uh, other elements like as usual, and the last element the next portion of the last element or the successor of the last element is the first element. So while traversing the linked list, what we have to do is we just have to say where is my head, and we find the head, then we traverse like this 2 5 7 8 10. Now 10 points to 2 again, so this is, we will be revolving in a circular manner, so that's why it is called circular linked list. So circular linked lists are also very known data structure in computer science, and these are used for developing circular buffers and all. So but we need to be very careful while using circular linked list, because we might end up in an infinite loop, because there is no terminating condition here, because there is no none of the node is pointing to null. So if we keep on traversing a linked list, and we need to set proper conditions before our loop get terminated, so we need to be very careful in that. So we have done a lot of coding in this session, and we have seen a lot of code. So based on these codes, I want you to try this examples or try these problems on your own. First problem is write a program to print linked list in reverse order. So uh, you need to print a singly linked list in reverse order, because we have already covered how to print a doubly linked list in reverse order, and it's very easy. So just try your hands on printing a singly linked list in a reverse order. Write a program to search an element in a linked list. So this requires you to traverse through the linked list and find a particular element. Write a program to check if a linked list is a palindrome or not. So palindrome is like if we reverse the linked list, the elements will match each other. So like 1 2 1 is a palindrome. So if we reverse 1 2 1, it will be 1 2 1 again. So it's a palindrome. So you need to find if a given linked list is a palindrome or not. So the first problem, that is reversing the linked list, will help you in solving this problem. Next problem is write a program to check if a linked list contains duplicate element. So here you need to extend your search program, or the program that you will be writing in the second question of searching a element in the linked list. You need to extend that program, and you need to run maybe two loops, or write your own algorithm to check if there are duplicates in the linked list, and you can say okay, there are duplicates in the linked list. If you are more interested, you can perform removing the duplicate from the linked list, so that will also give you more understanding on how to operate a linked list. So this brings us to the end of this session. I hope you enjoyed this session.
I'm sure you enjoyed learning from this video. Please like the video, and if you have any doubts regarding this video, please comment us in the comment section, and don't forget to subscribe to our channel for more such informative videos. Do look out for other related videos in our playlist. For more information, visit our website now. Keep learning with Intellipaat.